Hi there, in this video we're going to derive the Fourier transform. Now from the previous video we've seen that we worked out the Fourier series representation of this square wave. Here. We've seen it from this square wave here. Now the time domain representation is a purely real function. Now we tend to only think about real functions of time. There may be other instances in other branches of physics like quantum physics and things where we may look at time as being a complex valued function, but for our purposes here, time is purely a real function. Now this square wave here has a period t0, okay, and this distance here is tau, okay, the actual pulse width is tau. Now we went through the derivation on the last video and we worked out that the height here, okay, which is we'll call Cn, okay, the height here is given by this function here, tau upon t0 sine a half omega naught. It's actually an n there as well, n tau upon a half omega naught n tau. Now when we draw that out, and I've drawn it out in 3 dimensions because unlike the time axis, unlike the time, the frequency is a complex valued function, meaning it has an imaginary part and a real part. Now it so happens that this function here is an even function. Now an even function will give you a purely real value in the frequency domain. Again, I'll go over that when I go over another video on even and odd functions. So we end up with this envelope here, okay, and we have these individual frequency components which are multiple integers of some fundamental frequency. So that's a fundamental frequency there, and the integer multiple is given by the value n. Okay, now the interesting thing about this is the height here is given by tau upon t0, so the height is given by the pulse width divided by the period of the pulse. Now I mentioned it in the last video, but it's interesting here and it's useful for the derivation of the Fourier transform. But if we were to take that function and we were to shift it along the time axis, okay, so now we've moved the function to this point in time, we still get the same pulse width and period, but it's just been shifted over. So now the function is it's not an even function, it's not an odd, so it's a mixture of even and odd functions. Okay, so when we go and we find the Fourier series representation of that, as I mentioned before, when we shift it in time, what we're doing is we're allowing these phasors to now to move, okay, within their circle. Right, so in this instance here, the result is a purely imaginary function of frequency. So now we're not sitting in the xy plane here, we're sitting in this plane here. So the phasors in effect have just shifted round, apart for this one here, which is centre one, which has remained as a DC value or as a fixed value. So these have all moved, okay. Now as this here moves further along until eventually we end up back at the same position where this pulse here has moved over to this position here, then these would have been all the way around 2 pi and we're back in the original position. Okay, so a shift in time will give you a shift in phase in the frequency domain. Okay, now we can see that there. If we had some function of time, and it's just we'll make it one value for the phasors. Okay, so it's some Cn e to the in omega naught t, okay, then if we were to rewrite this out as a delayed version, so it would be f of t minus some delay tau, then we're just by the math, simple math, it would be c to the n e to the in omega, and it would be t minus tau instead of the t, and when you multiply those out, it would be cn e to the in omega tau times e to the in omega t. So the cn here can head over onto this bit here, so you just end up with the cn e to the in omega t, which is just our original function f of t, and we have an extra term e to the minus in omega tau. So we ended up with a function here, original function, and we ended up with an e to the in omega naught tau. So that e to the in omega naught tau is just a phase shift of a value tau. Okay, so the main important thing here is that the time domain is a real valued functions only, okay, but the frequency domain can be complex valued functions. So given that, we'll move on to the main part, which is our derivation. Now again, I've written this out already because just doing it live, you end up making mistakes and I don't get it as accurate. Okay, so what I've done here is I've drawn that square wave. Okay, so I've drawn a square wave there with a particular period. Okay, so there's, you say there's a period there, okay, in this instance, okay, and again that's just some function of time. Okay, now again this is just the envelope which it's been created, so that's the same as the envelope you've seen just on the previous page, and the height of that envelope there again was tau upon t naught, and those were passing over at 2 pi n, I think it's tau upon t naught, is it? I'll have to check and see. I'll come back to that. I can't actually remember if it's what the crossover points are. I think that's right. So the crossover points are going to be the same for all of these. Okay, now just go back to here. This one here, when I do that's the Fourier series representation of that. Okay, now if I delay this in time, okay, by one period, okay, then what's going to happen is one period, sorry, half a period, then what will happen is we'll get the same number of phasors here, okay, but some of them will have rotated round about 180 degrees. Okay, so this one remains the same, that's rotated, that's the same, that's rotated, that has rotated, and that's rotated, that's remained the same. So you can see these ones haven't rotated. So if I was to take this function here, and of course it's the same height, okay, so it's the same height envelope, it's the top and t naught, and the crossover point's the same. So if I were to add these two together, okay, then I would get this thing here, and it would be a function, okay, whose period has been halved. Okay, so that's a period there in this one, and that's a period here, t naught in this. Okay, so you get twice as the number of components here, so the period there has been halved. So in effect what you want to do is we can take this and add it onto that. Now when we do that, some of the terms add up. For example, this term adds up with this term here, and you get a term of double the height. Now if you come along to the next term here, then we have this one adds with that and it disappears, okay, because that's a positive and that's a negative. The next one, both of them add up. In effect you can see these are adding up constructively, okay, and we're going to get holes where they've added up destructively, I suppose you could call, where you've got a positive term adding to a negative term. So you're going to have half the number of components here, but they're going to be twice the height. Okay, now that's just a a graphical representation of what's happening, but it gives a motivation as to what's going to happen whenever we double the period. Okay, so the period is this point, this distance here, and this one up here, the period has been doubled. So when we double the period, we go for this graph here up to that one. So when we double the period, we double the number of components, but we half the height, and you can see that obvious because the height there is given by top and T naught. Tau is fixed, and it's the pulse width, but T naught there in this instance is doubled. Okay, so if T naught is doubled, then that height has halved. Now, if we take that to a further extreme, if we increase the period here and we say, well, let's let the period here tend towards infinity. Okay, now I haven't actually shown it there. I've shown actually a couple in, but you can get the gist. You're going to allow this to head off to infinity. So that you're going to end up with is, and as that tends to infinity, you're going to end up with an infinite number of these components, but the height of them will actually tend towards 0 because the height is given by top and T naught, and as T naught tends towards infinity, this top and T naught will head towards 0. So it's not very much use in that form. Okay, so again we've just wrote out the actual equation for it. It's given by this here. Okay, so the actual amplitude is given by these two numbers here, top and T naught. So top and T naught tends to 0 as T tends to infinity. But and here's a little the coup de grace, I suppose. If we were to scale this by a value T naught, okay, so instead of looking at Cn, if we looked at Cn T naught, okay, then in this instance here we would have tau upon T naught times T naught, then it would mean that the height of this thing here would remain at a fixed value of tau no matter what value you had for T naught. Okay, so as T naught tended towards infinity, we still just have the function tending heights of each value tending towards some value or a factor of a value tau. Okay, so what it means constant tau. Yeah. Okay, so that's one thing that occurs. Okay, now what else is going to occur? Well, we already really mentioned this is T naught Cn will actually tend towards, instead of being just a single, just individual values, okay, of value n omega naught. In effect, the value of n will increase, okay, as we double the period. The number of phasors doubled, and if you keep doubling and doubling, and if the period tends to infinity, the number of these components tends to infinity. So if the number of components tends to infinity, then this envelope here, the Cn envelope, it will tend towards a function, okay, a continuous function. So it will be a continuous function of frequency omega. So now we would no longer have an In omega naught here, we would just have an I omega. Now another thing to note is that the only reason why you put the I in there is just to signify that the frequency is a complex valued function. Okay, so it could be real, it could be purely imaginary, or it could be a complex value. Okay, so we noted then, as we say, the number 2 as n tends to infinity, as n tends towards infinity, as T naught tends towards infinity. Okay, so it means that the number of components tends towards infinity, so we tend towards this envelope f of omega. Okay, so we end up with a function there. Now, another thing that we can note is that the integration limits. Now, the integration limits, because the function here 10 is 0 outside the actual distance. Okay, the not the period, the, the, the width, the pulse width. As the period tends towards infinity, all this out here tends towards 0, so that's all 0 and that's all 0. Okay, so it means that you can change, you can create the, the limits of the summation, and you can change them to minus infinity to plus infinity. Okay, so we'll see all that in a minute. So we had our, if it was our, what we've seen is our dot product, so we're looking for the frequency components, or values of Cn, okay, and we get the Cn by taking the dot product of the function with the orthonormal basis here, okay, and what we want to do is we want to see how this changes, okay, so this is going to change because of what we've looked at here. We're going to multiply with this value t0, and we're going to let t0 tend to infinity. So originally the equation was written in this form here, okay, so that's just the Fourier series, the complex version of the Fourier series, and in fact that's the complex version of the dot product. So we now have, instead of Cn, would be t0 Cn, okay, so t0 would cancel with t0 here, okay, and we would have f of t to the I n omega naught t, but that n omega naught, that's the same as saying n2 pi upon t0. Now we know that t0 tends towards infinity, so this whole value here, n omega naught, is going to tend towards a fixed value, okay, because the n tends to n gets very large and t0 gets very large as well, okay, so this tends towards a one fixed value omega, okay, and so this would be, when it wouldn't tend to 0, tend to some value, okay, so I can say omega tends to some constant value, okay. Now that means we can rewrite that equation as, instead of this t0 Cn, we can write that as a function as I omega, because now omega is a continuous value as opposed to being a discrete value, and our summation limits can change from 0 to t0 to minus infinity to plus infinity, and the function of f of t and our n omega naught will just be replaced by our value omega by dt. Okay, so that there is going to be the forward transform. Okay, it takes the time domain and it produces a frequency domain representation. Okay, now we're almost there, so that's sort of half of it done. So now we're going to look at the other part of our equation. So our original Fourier series was written like this, and we're saying we want to approximate a function f of t given an orthonormal basis of sines and cosines, which is our e I n omega naught t, and that's going to be the scalar coefficients of them. Okay, so now we're able to say f of t is going to equal, well, we're now dealing with, instead of dealing with Cn, okay, we're going to be dealing with it would be t0 Cn. Okay, so it means that we'd have, in order to get back to the original function, we'd have to divide it throughout by t0. Okay, so you're going to end up with 1 upon t0 times this here. Okay, but you can write t0 and this term here, because so omega naught equals 2 pi upon t0, so the 1 upon t0 is omega naught upon 2 pi. Okay, So it means that you can then replace that t naught by 1 upon 2 pi. Okay, and then the omega naught here can come in here as well. So that's, we'll just take an omega naught over here into the summation. Okay, so now we can say as our value t naught tends to infinity, then our omega naught will tend to our value d omega, okay, which is a small value of omega, and the summation is going to tend towards an integral sign. Okay, so then we can write out this here is now going to become f of t is 1 upon 2 pi, the integral from minus infinity to infinity, f of omega e to I omega by d omega. Okay, now that's a derivation of the forward and inverse transforms, a derivation of sorts. I mean, it gives a good, it gives a description, a graphical description, but it's a kind of a heuristic description of how it's derived, because it's heuristic in the sense that we've derived it given one particular function, okay, and we're assuming that every other function that would behave in that manner as well, but it does give you a decent lead in. But what's more important is the interpretation of what you have here, because as I say before, you tend not to, well, I tend not to remember a lot of these derivations, or even make an effort to memorise them. You know, I've got more interesting things to stick in my head. But what is important is the understanding of the interpretation of it. So that's what I've tried to do in this last little bit here. So this last little bit I think is probably the most useful. Now we go back again, and I'll go back to the beginning, and we'll go over this here and we'll talk through it. We've got a function of time that we want to approximate, and we want to approximate it using a series of sinusoidal functions. We've gathered the sinusoidal functions into a complex exponential. It makes the maths a lot simpler. Okay, now with this here, if we think about this here as forming an orthonormal basis, okay, and we're looking to find the scalar components, and we don't know how to find the scalar components, so then, but we have a method. Obviously the method is that we have this as an orthonormal basis, we produce a dot product that ensures that that basis is orthonormal, okay, and from that, and that's the dot product here, and from that dot product we can take the dot product of the function with the orthonormal basis and find out our values of our coefficients. Okay, so it's a bit of a mouthful, but coming back down here, it's just analogous to saying we've got a vector A. The vector A has got scalar components, and it's got a basis there, and we take the dot product of the scalar components and basis, and that just gives us our vector. So that would just give us our vector A1 E1 hat A plus A2 E2 hat plus A3 E3 hat. Okay, and over this end here we're looking to find our values of our an. Okay, so that a is the same as a function, an is the same as this function here, and the e hat n is the same as your orthonormal basis here. So we're looking to find our values of an. We find the values of an by taking the function f of t, okay, which is that function there. Take the value f of t, and we do the dot product, but this is the dot product here with our orthonormal basis e to the n. Okay, so that then gives us our values of an, and that's our values of an here, which is our frequency domain representation. So that there would be the forward transform, and of course the inverse transform would be would be very simply saying, well, how do we generate our function here, our vector A? Well, you generate a vector A by taking your values of an, which you have just found here, and just multiplying it again by the orthonormal basis en, and you get back to your vector A. So this lot here in simple linear algebra is directly analogous to what we're doing here in the Fourier transforms. Now, a couple of other things. We've got the factor of 1 upon 2 pi. Again, that goes back to the idea of normalizing the vector space. Okay, so we've seen that in quite a few of the other videos. And the other thing to note is that in here we have our e to n, which is our orthonormal basis, but we've also got an e to n here, which is an orthonormal basis. But now our orthonormal basis, one has got a positive sign in it and one has got a negative sign in it. Now you can see that the reason for this coming out as it does is really down to the fact that if you had two vectors and they were real, and you wanted to find the dot product of those vectors, you take this sum from I equals n equals 1 to I of a n to b to the n, okay, and that would be your dot product. Now that's assuming that both of these are real, okay, but if they are complex, okay, so they've got a real and imaginary part to them, then the dot product is going to be defined as the value, it's going to be an times the complement, or sorry, the conjugate of b to the n, okay. So we would have to define the dot product in that format in order, if the values of a and b are complex, okay. So you can see then that what would happen is, in fact, I think I've got it in the next page. Put it in. Let's see. This is the last little section here anyway. This is us pretty much done. There you go. So we're only dealing with real valued functions of time. Okay, we're dealing with complex values of frequency. So if you were to find the Fourier transform of a function, and you it ended up being a complex value of frequency, in order to get back to a purely real value, you'd have to get rid of all of the complex values, okay. So the only way to get rid of the complex values is to ensure that they all add up to 0. So make sure they all add up to 0 by taking the conjugate. So the conjugate of a complex number, if you have an imaginary number plus I, the conjugate would be minus I. Okay, so that's what the minus and the plus do here. Okay, they ensure that the complex values are conjugated, so that whenever you go back to the time domain, you're always going back to the a purely real function. But that just comes out via the maths, and it comes out via the maths because we start off with a purely real valued function. Okay, so that's all that really comes from. Now that's all for this video, and I'll get back to you in the next video. Thank you. Goodbye.